Okay, hello. Good afternoon, everyone. Hello, Konstantina. Thanks a lot for the introduction and for giving me the opportunity to be here today. Unfortunately, I missed the morning session, so apologies if I do repeat things that were covered already, but I'll try to be fast on these. Okay, so indeed, my talk will be a little bit, well, not necessarily only higher layer, but more generic, I think. So I will not focus so much on one particular topic, but would like to give you an overview of what we have been concentrating on over the past 7 years or so at the university, and specifically our group. Okay, brief outline of the talk. I will start with the discussion on 5G and beyond 5G vision and the related services. Then I will concentrate a little bit on the proposed 5G and beyond 5G architecture. And I will put a little bit of emphasis on some, if you like, adoption or application of optical networking in support of 5G and beyond 5G vision. So I'll try to say a little bit about how one can use optical networking to interconnect 5G RAN and compute resources and so on, which are an integral part of the overall architecture here. I will talk a little bit about some dynamic resource management schemes we're working with, and then I will move into describing some demonstration activities that we're doing as part of some of our European projects that we're doing in collaboration with a number of partners, some of which are in fact in this room. And then I will conclude. So to start a little bit with the vision, if I go back maybe 7 or so years ago when we started talking about 5G, some of us that were heavily involved in European activities, the 5G public-private partnership of the Commission. We had a lot of discussions trying to, if you like, shape up the vision. And the idea was to create, to have 5G creating new business opportunities for a large variety of industries, and this going beyond ICT, so a number of what we now call vertical industries. So the idea is to come up with a solution, with a technology, with an architecture that can support not only the ICT, but also a number of other industries. And also one fundamental principle was to actually create a network that is future-proof. So the next generation will not be something completely new, but it will take advantage of this architecture that will be evolved to the next generations, and it will not be replaced. So that would basically mean that beyond 5G will bring incremental advancements. And another fundamental principle was to have one common solution that can support both operational and end-user services. And under this framework, we see part of the services that were mentioned also in the previous talk. So, for example, massive machine-to-machine type communications, of course, enhanced mobile broadband, and ultra-reliable and low-latency communications. And if we try now under this framework, if we try to identify the trends when we go from 5G and beyond 5G, we can see that there are specific technological pillars that the overall architecture has been based on. And this involves, first of all, extreme technology heterogeneity. So we need to integrate together different network technologies. And this involves the most advanced solutions that you can think of today, together with some more conventional and traditional solutions, wireless, optical, satellite these days. And this is one part of the heterogeneity that we have to deal with. And the second part has to deal with the integration of network and compute resources. Now, looking at one infrastructure that commonly addresses requirements for compute and network resources is quite fundamental in the context of 5G and beyond. Another fundamental principle that 5G has relied on is this one, softwarization and programmability. What we have is a paradigm shift. So we're moving from what traditionally we had in networks in the context of network entities to network functions. And we also have to define interfaces and protocols that will allow this model, that will allow network functions to be configured in software, and we decouple control and user plane. Another fundamental pillar in terms of technology incorporated in the vision of 5G is this of the slicing and virtualization. Sharing is very important. We need to have the tools, the technical tools, to be able to share infrastructure and enable models that allow multi-tenancy. So we want to have multiple tenants that can use the same common infrastructure, and this is very much the essence of the vertical industry support. So we want to have this one common infrastructure that can support a number of very different industries with very different requirements and very different type of services. And we migrate towards artificial intelligence and machine learning. Of course, you are all very familiar with this. The adoption of ML and AI techniques is increasingly becoming important in order to be able to optimally manage infrastructure resources and support the service requirements we have. And more recently, we also see, well, this is some work that is going on for a while on air interfaces, so unlicensed bands come into place, millimeter wave, terahertz frequencies, and so on. And in fact, the focus changes from migrating to long coverage solution to spectrally optimized from spectrally optimized solution to improved also coverage solution. And we see also technologies like massive MIMO. I saw there was a talk on RIS this morning. So these are technologies that are coming more and more important, requiring advanced beamforming techniques and other technology advancements in the area of wireless communications. If we look into the status of standardization, we can see that it's quite mature as far as 5G goes, and I'm sure this doesn't surprise anybody. So basically, we have the activities under 3GPP and ITU 5G, and we see that 5G studies, my colors are not coming up very well, but 5G standardization activities are here. So until release 16, for example, and then beyond 5G, we go for release 17 and on. So you can see that these are quite mature. There's quite some activity on beyond 5G, and of course the activities on the 6G follow back in time. I would like to now go into some discussion on 5G architectural considerations. I will start with some really, really simple principles that everyone is familiar with. So if we try to look at the mobile network from a functional architecture perspective, of course, you see your your end users, you see your RAN, your radio access network, you see your transport network, and you see your mobile core. And this is independent of the generation, right? These are the functional blocks that you have there. And okay, what happens in the radio access network is you have your radio heads and you have your base stations, and this can change in terms of terminology and so on, going to from 4G to 5G. But functionally, these are the different elements we have, right? Independent of the technology. And what happens from when the discussion of 5G comes into play is we have, if you like, a little bit of a change in the model. So the functional blocks remain, but we have transformation of the core network and separation of the user and the control plane. This is something that 5G brought. And then we have one common network, and this is one common network, one common core network, and this is a common network to support both 3GPP and non-3GPP elements. And the overall idea is, I'm told that I have to move, so sorry. And the overall idea is that we adopt this softwareization context. So this can be very well served through the service-based architecture. So the overall model we adopt in 5G is service-based architecture, where architecture elements are, what I was saying before, network functions. And they offer services in support of the user service requirements we have. And this is done through interfaces of a common framework. So it's really, really important to identify the details of the interfaces we have to support the connectivity requirements we have. This architecture model is chosen to enable deployments and take advantage of the latest virtualization and softwareization technology. So in fact, as I was saying before, is the mechanism to be able to transform the network and take advantage of network functions rather than network elements. Get functions out of the resources we have. Right. you're all familiar with the BBU, the baseband unit processing. This is with the good professor here, we're discussing about BBU processing and how you can offload BBU processing away from remote radio heads about 10 years ago, I think it was. It has gone a long way since. So basically the idea is we have a set of functions that are part of the BBU, and there is well defined now in the standards that you can split the different functions, and you can allocate the different functions at different locations in your network, closer or further away from your radio head. So you can have well, the early version, and I have a slide further down that will show you this in a moment. The early version was offload everything remotely, right? And then that was traditionally a front haul CPRI type of solution. But then the next generations gave us the flexibility to split the functions and decide which ones we want. Well, of course, abiding to the order, right? Decide to allocate some closer to the remote radio head and some further away. And if I try to summarize this historically, this is the early version where we had the front haul offloaded, all the processing offloaded somewhere further away from your radio unit. And the connection here was supported through this front haul CPRI type of connection. Now, this was good because you were able to relieve the requirement for high computational resources close to your radio head, and you had a lot of these, so it's a saving. But the problem was that you now needed a very strong, if you like, a very powerful transport network to support this. This was a big constraint. To deal with this problem, the next generation, the next evolution gave us the idea, the capability to split, right? And decide which part of this stack of processing will happen close to your antenna and which of this can happen further away. And there were some, and there was this split option 2, which gave you this intra-physical split, which basically enabled you to do part of your physical processing close to the antenna and the rest of it remotely. And then you would have quite significant benefit in terms of computation here, but you would alleviate, you will reduce your transport network requirement a little bit there. And we move from this, so this is clearly 5G, right? So we move from 4G to 5G, and then from 5G, we go to the next generation, which is the 5G ORAN, Open RAN solution, which gives you the capability of what is known as disaggregated RAN. So basically what you can do is you can play with the split, you can decide what you can process where, but you have an extra degree of freedom, and you don't have to do it. You don't do the split only between 2 points, but in fact you do it between 3. So you have your RU that has some capability of processing, you have your DU, distributed unit, and your central unit. And these are connected with specific interfaces that are well defined. Okay, and then I will try to say a little bit about deployment options. So if we have this model in mind, we can see that we have several deployment options we can support, and this and here this is G-Node B. So basically, is what we call in 5G is the next generation of E-Node B, and it involves all this RAN capability I mentioned before. So you have all the BBU type of processing, and you can decide to do this monolithically in one device. And then what you have to do is connect your G-Node B with the UPF, user plane function. This is an element that addresses user plane, but also is part of your core network as well. And then the connection between your UPF and the external data network. And connectivity between G-Node B and UPF is supported through your transport network. And the transport network here plays the role of a backhaul network, right? So the support of your transport network here is only as a backhaul. And so you also have backhaul connectivity between your UPF and your data network. So all your functions, CU, DU, RU that I showed you in the previous slide reside here. Right. And of course, yes, this deployment resembles the model of LTE that we're all familiar with. Now, an alternative deployment option is what you see here, when you can actually split the functions, the RU, DU, and CU functions, and you can decide to locate RU close to your antenna, and your DU and CU, they can, for example, be collocated at one location. And then you have your ORAN front haul connectivity between your RU and your DU-CU element, and this is what we call front haul, right? And this is, again, part of your transport node, but these nodes will only support front haul type of services. And then we go from the DU to the CU, the DU-CU element to the UPF, and the connectivity here is, again, through your transport network, but your backhaul type of nodes. And, of course, from UPF to the data network, backhaul type of nodes. And I won't go on with this for too long, but I would like, just for completeness, to show you the other option. So you can have your RU, DU at one location, and further away your CU. Again, connectivity here is front haul type of connectivity, and from your CU further is backhaul type of connectivity. And then we go, and I promise this is the last one, and then we go to the most flexible architectural model, where we have this disaggregated RAN concept, when you can actually deal with your processing elements at different locations. They're actually physically allocated at different geographical locations. So you have your RU, and you have your DU and your CU, and you have special interfaces that allow you to connect, and protocol implementations that allow you to connect from one to the next. And here you can have and you have to have quite a strong, quite a powerful network that can be either wireless or optical. So you can see millimeter wave type of solutions and so on, but also optical solutions very commonly. In fact, we have been working with optical transport solutions, and I mentioned this at the beginning of the talk, a little bit at the introduction. So here we have been deploying optical networks quite heavily to be able to provide the connectivity requirements we have. I mentioned UPF before, which is the user plane function. What does this do? It provides connectivity of the 5G system with the external data network and acts as a stable anchor point for the devices towards external network. So you always have to go through that one point to access the external world. And if there's user mobility, this is in fact the element that hides the aspect of mobility associated with this particular RAN. And of course, all this discussion so far concentrates on the user plane, right? So the plane where the actual data, user data is supported, but we all know that a network like this requires extensive and intensive control, right? And the control is supported through the core network. And here you see the whole architectural layering, just to use Konstantinos' terminology. So basically here you see the user plane, and here you see the core, your 5G core functionality. And 5G core now is slightly different to what we have seen in 5G. It's very much based on the concept of functions I mentioned before, and I only give you some examples of some important functions, but in fact, this can be more extensive than what I have here. So this model is in accordance to the software-based architecture I mentioned before, relies very much on the concept of functions, and some of the important functions is, for example, the access mobility management function, which supports encrypted signaling, registration, authentication, and so on. When the service is initiated. The SMF management function, which manages establishment, modification, and release of individual sessions. There are other functions, like, for example, this NSSF. It's the network slice selection function. And this is responsible to enable the creation of end-to-end slices, which is a fundamental concept in 5G. And also we have functions like this NDWAF, Network Data Analytics function. This function enables the adoption, if you like, to bring all this AI intelligence in the 5G core. So this happens through this element. And one can appreciate that there are quite a few interfaces that we have to support both user plane, so all these Open Run front haul tunneling, F2 tunneling, and N3 tunnels, and so on. So quite a few interfaces to handle user plane functionality, but even more to deal with communication requirements for 5G core. So you see all these N1, N2, N4 interfaces. So a big part of the architectural description is to identify the details of the interfaces here. Okay, now we looked so far into the 5G architecture taking a network-oriented approach, right? We looked into connectivity and so on. But I mentioned at the very beginning that compute plays a big part in 5G. And this diagram tries to give you a little bit of this flavor. So what we have here is the same architecture that I showed you before, but with a little bit more, if you like, focus on the compute side. And it gives you the capability the overall architecture has in handling processing. So depending on the services and the service requirement we have, we may want to do processing relating to the 5G core itself. So support 5G core functionality or even application type of services. We can handle these compute requirements either at the central cloud or through MEC type of solution, edge type of solutions, right? And the overall architecture allows for this. So it gives you the option of this local breakout that you see. So you can drop and handle all of your processing requirements very close to your RU in a private type network environment. Or you can go through a transport network to another MEC type of solution, but somewhere further away from your RU. And if you have no delay constraints or your privacy constraints, then you may decide to even handle your processing requirements at the central cloud, somewhere far away, shared, a cloud that is shared with other users. Okay, now I will try to, I don't know how well I'm doing with time, but I will try to say a little bit about some of the activities we have in our group, in our lab. So I will give you some examples. It's not exhaustive of the work we do. Focusing on optical networks in support of 5G systems and beyond. Okay, so here what you see is a monster, is the transport network I was simplifying in my previous slides. Now here is a far more complicated structure. So this is a transport network that can support the disaggregated run solution. So we have transport nodes that are able to handle jointly front haul and back haul services, because this is the ultimate flexibility type of model, right? And functionality, the ultimate functionality model. So this is what we propose, to have common transport nodes to handle both front haul and back haul type of functionality. So this structure is there to support this. And then we have the capability to do processing either through a MEC type of environment or central cloud type of environment. So the key challenge we have to solve is the fact that we're trying to have common nodes, a common transport network that supports front haul and back haul services. This brings constraints in terms of capacity and also delay and synchronization requirements. Optical networks appear to be a very promising solution to do that, and we have been working on this for very many years. We also need to provide a solution that can offer converged network and compute services, and of course, the underlying principle of disaggregation of resources, not only for the RAN, but for the overall infrastructure. So we're looking into bringing concepts like compute disaggregation and so on. Now, to do that, you need to have a very flexible optical transport node. Here you see the architectural description. I don't want to say very much. This is an architecture that allows you to handle multiple wavelengths per fiber, and you're able to have switching granularity at sub-wavelength level. So you don't only switch wavelengths, which you commonly do in optical networks, but you can actually switch time slots, which fits much better the 5G vision, where the granularity requirement is much higher than usual optical networks. Okay, and here you see what our optical transport nodes do. So basically you can have incoming traffic that you can decide where to direct, either, for example, to go through this local breakdown I mentioned before and reach your local MEC type of resources in a private type of network, or be able to follow a different path across your network, possibly to reach a central cloud type of resource. Of course, to be able to do that, you need to have the correct transport solution. And what we are using for some years now is a proprietary solution that was developed by the University of Bristol. And we have used this in several generations of 5G projects as a future-proof optical transport. We call time-shared optical network. What that allows you to do is to deal with variable optical frames supporting what I mentioned before, sub-wavelength switching granularity. So basically, we're able to create optical frames that we can switch individually and handle the allocation of bandwidth in time slots. Another feature of this technology, which is really, really very powerful and fits very well the architectural positioning of 5G, is the capability to allocate optical bandwidth elastically. So here we don't have a fixed grid solution. When we assign optical bandwidth to a user, this bandwidth can be variable, and we can decide on the fly what this has to be. So if I have a very heavy front haul type of service, then I can assign a bigger chunk of my optical spectrum to this. And if I have a really light sensor type connectivity, then I can assign a really tiny small of my spectrum to the service. And for 5G, this is really, really important to be able to do. So this technology can actually do this. And then it can also address efficiently, in this context, these varying bandwidth requirements of 5G services. Right. So in this context, if I go to the architectural model I was describing before, you can see my end users are here. My RAN, my radio access network is here, and there you can see my processing elements, DUs, CUs, and so on. So we consider a 5G network which interconnects a set of RUs, DUs, CUs, UPF, providing connectivity of the user to the external data network through these elements. How do we do that? We do that creating end-to-end service flows. Now, end-to-end connections can be successfully established if we have the required optical network resources, right? Remember, transport network plays a key role for this connectivity. So we need to have optical network resources there. And what are they? They're wavelengths, right? Of course, it's fiber connectivity to start with. Second level wavelengths. I have multiple wavelengths per fiber. Then for every service and every flow, I need to identify the specific wavelength with which I support my flow. And specific time slots, right? Because not only I assign wavelengths, but I also am able to share my wavelengths between time slots. So this is the problem I have to solve. I have to solve this problem across my end-to-end path. And this can be solved by solving an ILP model. Okay, the objective is to maximize a utility function, which maybe, for example, keep maximum unused resources. So provision your services, minimizing the resources you use and maximizing unused resources, considering both network and compute elements. So when we provision, when we try to identify required resources, we look both at the network and the compute requirements. And we need to, of course, do that by making sure that we don't, if you like, ignore any specific constraints there may be. So we do that subject to end-to-end connectivity constraints, and one of which will be a specific order of the service chain. So I cannot change the order of the execution of the functions, right? So I have RU, DU, CU, UPF, and data network. These are the functions I have to execute, and they have to be executed in that order. I also have demand constraints, so the available resources I have. So I have to also deal with the allocation of wavelengths and time slots to the appropriate interface at each time. And how do we do that? Through joint routing, wavelength, and time slot allocation. Here you see the details of the architecture again. So basically you have your incoming services that you need to allocate, the incoming traffic that you need to allocate to your resource blocks, if you like, associated with your optical node. Now, this problem to solve in an end-to-end fashion is actually quite computationally intensive. So we split it into smaller sub-problems to be able to handle it. And the first stage, we estimate the total number of demands to be served within a specific time frame. We solve the routing and wavelength assignment problem per connection in order to identify the optimal path in the network. And of course, this path involves a number of switches and a number of links. And then the flows are transferred. So when we establish the path, we can transfer the flows from G node B to the destination UPF and the external data network. To do that, in our studies, we estimate traffic through some traffic statistics we have from an area in Bristol. Then we have a network topology to which we map these traffic statistics, and we relate them with specific services. The second stage problem we have to solve is once we have the end-to-end connections, once we understand the path and we have the wavelength allocated for that path, then we have to do time scheduling on an optical frame basis, on a packet, if you like, the equivalent of a packet basis. And to do that, you can apply different policies, right? You can think of many policies. We have here two simple examples. First fit. So basically, you look at your grid and the first slot you find available, you allocate the demand, or best fit, right? So you try to see which slot is the most resource block is the most efficient block for you to use. Now, the different policies have different performance. So we use an intelligent way to actually pick the optimal policy to apply. And this we have found that is very dependent on the traffic characteristics, on the status of the network at that point in time. So we can the way we pick the policy is through machine learning. So we have developed a neural network solution that, based on the status of the network at the time, picks the optimal solution to allocate, to do the scheduling. The data set we used to train our models is data that we have collected through an emulated environment in our lab running 5G platform. In fact, and here you see some of the traffic statistics. So this is UE traffic, network traffic per UE that has been collected from our platform in the lab. We have a private cloud solution, and we have two different 5G platforms that have been deployed. Open Air Interface, which was developed from Eurecom in France. So we are working very closely with them, and of course it's an open platform, so everyone can use. And the solution we have deployed is a standalone 5G solution. We have also deployed the free 5G core, also a standalone solution. This is only for the core. Open Air Interface includes both RAN and core. Both platforms have been deployed in virtualized servers, and we are using these to do detailed profiling of computer network resources when we run over the platform different set of services. Right, so just to give you a better idea and map the implementation we have in our lab with the architecture I was saying before. So basically this is the architecture I showed you before. What we have done in the lab, we have virtualized servers that are hosting the two platforms I mentioned before, comprising both the 5G RAN and the 5G core solution. These are supported by VMs that are hosted at physically separated servers. We have a VM that hosts the end user services, which is hosted at a different physical server. And the transport network we have in the lab is an optoelectronic type of transport network, so optical links, and both electronic and optical switches for the switching nodes. Okay, just to give you some idea of our results, here you see the utility I was mentioned before, and what you see is how the system performs in terms of, so we want to maximize this utility, right? So we want to have, so what we see is the results we get with best fit, the results we get with first fit, and the results we get with our solution. So what you see, our solution matches the best and you can see that the different options, best fit and first fit, have different, if you like, optimal areas. For the when we have low traffic conditions, first fits operates better because of its low computational cost, while best fit operates better for high loading conditions. And if you can adaptively choose the best one every time, of course, your system performs in the optical way across the range of operation, right? Okay, and do I have a few more minutes? I would like to close this. Okay, I'll be very fast. I would like to close this presentation with some demonstration activities we have. We are at the University of Athens, and myself personally have the technical coordination of a 5G project called 5G Victory. It's an ICT 19 project. The title is Vertical Demos over Common Large-Scale Field Trials for Rail, Energy and Media Industries. The project duration is 3 years. So in theory, it was ending this summer, but we took a 13-month extension, so we're finishing in a little bit longer than a year from now. The project budget is 13.5 million, and it involves 26 partners across Europe, one of which is Intracom. So I have some of my colleagues from the project sitting in this room, and I will try to say a little bit about the demonstration activities that we have. The project focuses on, proposes an open architecture that will allow to showcase the fundamental principles of 5G. So to show how 5G can support a variety of vertical services and vertical industries. I'm not going to go into the detail of my slides because Konstantinos tells me that I don't have so much time left. But I would say just one thing before I move to my next slide. The 5G Victory was proposed the adoption and extension of the existing ICT infrastructures in Europe when we started. So we stepped on, we exploited the ICT 17 projects, 5G Vini, 5G Genesis, 5G Eve. These were the three infrastructures, 5G infrastructures funded by the European Commission, and we added 5G UK in the UK. So these were the test beds in which we bring in our activities. We have a variety of vertical industries for which we support services. I'm not going to say a lot about all of them, but a little bit about some of them. So we support enhanced mobile broadband under high-speed mobility, and the verticals here is transportation and specifically rail. Digital mobility, this is a cross-vertical use case between transportation and media. Critical services for rail, as the term suggests, is a rail type of service or use case. Smart energy metering. Here we have also smart factory type of use cases, but also cross-vertical between energy and rail. And finally, CDN services in dense static and mobile environment, which is a cross-vertical media and transportation type of solution. I wanted to show this slide because this is in Greece, and being here today, it's good to show that there are quite interesting activities going on in Greece. So in fact, this is Patras. The site in Patras exploits the 5G Vini site available on campus at the University of Patras, which is massively extended, and my colleagues from Intracom have really worked extremely hard for this, to support connectivity with our vertical players, being a rail operator and ADMIE, the energy provider that have locations there. And we provide 5G connectivity to them to support specific services. The type of services we want to support through this infrastructure is business services to train passengers, applying some of the concepts I explained before, and technology I explained before, and critical and performance services over the same environment. How do we do that? End-to-end slicing. So we have one common infrastructure that we slice and give slices to different industries. Here you see the connectivity across the rail track. So there is a fiber connectivity, there is capability for G-Node B base stations, quite a lot of millimeter wave of infrastructure. As I said, the Intracom has played a very important role in building this. Here you see the architectural approach. We have the the cars over the wagons of the train. We have two remote units on top of the one at the front, one at the rear. This is the stanchions across the track. And there's connectivity from the train to the stanchions through both millimeter wave solution and sub-6 gigahertz type of technology. And as the train moves, the connectivity migrates. And we have developed a mobility management element that, in fact, has two units, one on board and one at the 5G core part of the network. I understand my time is pushing, so I'm not going to go into the details, but I would like to say that the solution, the RAN solution on board the train is based on the disaggregated RAN idea I explained before. So we have distributed RUs, DUs, and CUs, one CU. And the connectivity on board is through a 10 gigabit Ethernet wired solution. The services we offer, I will move on to this. The services we offer, onboard video streaming services. This is through Cosmote TV content and the ICOM CDN platform that Intracom provides. We demonstrate service continuity for video on demand and near real-time streaming services through opportunistic bulk transfer. So basically the concept of data shower. When the train arrives at the station very fast, you can offload very large volumes of data. Okay, and we have a similar infrastructure in Berlin. This is based on the 5 Genesis infrastructure. Initially, the part of the 5G core, which was developed in the context of 5 Genesis, is hosted at Fraunhofer Focus, but the infrastructure has been expanded to connect to the Berlin Central Station. So what we have is connectivity of Fraunhofer Focus with the Berlin Central Station. We also have connectivity, 5G connectivity separately to IHP. IHP is the technical coordinator of the project, and they are located at Frankfurt Oder, is an area a little bit outside Berlin. What you see here is the setup of the infrastructure. Here we have the 5G core hosted at the Fraunhofer Focus premises. And here we have the solution at the station, Berlin Central Station, which involves 5G and R type of solutions together with all the equipment required for the connectivity of the train. In terms of services, I'll be very, very fast and I'm closing here. We have critical mission critical type of services, so train control signaling or railway telephony or transmission of CCTV data from the train to the Berlin Central Station. But we also have services to the users, like, for example, 3D content, 3D twin over their mobile phones that they can use to navigate themselves through the station or get advice for the remaining part of their journey. And also the capability to offload big volumes of data to support video on demand at the station, which is similar to what I mentioned before for Patras. I hope I didn't abuse my time. Thank you so much. Or your time.
Thank you very much, Anna. I find it an excellent tutorial for 5G network architecture and evolution, especially for us who are mostly stuck at the physical layer of the RAN. So this was extremely useful. I learned a lot. I have several questions, but we can take this offline. Any questions from the audience? Yes, Jimmy?
Yes, I was just wondering, you mentioned you had end-to-end network slicing, so it's both on the optical and also a radio access network?
Well, are you referring to the demo or are you referring to the... You're referring to the demo? Yeah,
you mentioned it with the Patras demo, right?
The Patras demo, yes, because I mentioned two things. I mentioned the lab exercise that we have, and there indeed we do end-to-end slicing. This is the objective. At the moment, we have, the demo is ongoing, so we have another year to go. So we have the slicing technology developed for the RAN through the NSSF function available in the 5G core. So this comes internal, if you like, inherently is the correct term to use. We also have the capability to slice the optical network. This is something else we can independently do, and the way we actually do that is through SDN control. And what we need to stitch together is the two solutions and provide this end-to-end service with 5G. And this is actually an excellent question, because it's not simple to guarantee 5G quality of service across when you cross domains that are not 5G, fully 5G controlled, right? So this is actually what we are concentrating on.
Okay, so do you have more info in your deliverables?
You can find information. We have some architectural deliverables that talk about end-to-end slicing. We submitted one quite recently, so and it's an open deliverable. You can find the first architectural solutions. It's D2.1 and 2.2, I think. And these are open. In fact, I had a link in one of my slides before. But the one which probably has more meat in the line of the discussion we now have, this is something we submitted very recently, and until we are reviewed and the deliverable is approved, it cannot go public. So if you're interested, I may keep a note and then send you a pointer when it's available.
Unless he's the reviewer, you don't know.
Well, we know the reviewers unless if they change them, yes.
Okay, any other question for Anna? All right, in the interest of time, let me thank you again very much. Thanks a lot.
Thank you very much.
Okay.